Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, everybody. Looks like we've finally reached a critical mass here. So I'd like to welcome you all to the session on verifiable computation, which is a topic that has moved from esoteric theory to practically near something that we will be doing in practice any time now. And it's been making this transition in a short, less than 5-year period. So it's a pretty exciting area to be working in. I'll be your host. I'm Brian Parno, and I'll be hosting you for the next 75 minutes. I'm a recent graduate from Carnegie Mellon, and I graduated about 3 years ago. I've been at the Security and Privacy Group here in Microsoft Research since that time. And I'll be giving you a brief overview of the field of verifiable computation, as well as touching on some of my recent work in this area, which has been focusing primarily on cryptographic techniques. Following that, we'll have Professor Michael Mitzemacher, whose group has taken almost the exact opposite approach. They've avoided cryptography entirely and instead focused on what are called interactive proofs. Professor Mitzemacher recently finished a stint as the Area Dean of Computer Science at Harvard University. During his career, he's published over 150 journal and conference publications on topics ranging from hash-based data structures, error-correcting codes, and data compression techniques. He's also published a textbook on randomized algorithms, and his paper on low-density parity check codes has recently won the ACM SIGCOMM Test of Time Award. Following Professor Mitzemacher, we'll have Professor Mike Wallfish from University of Texas at Austin. His group has also been working in this area, and they've actually been combining in a very elegant fashion. Yes, here he is, also right there. Professor Wallfish's group has combined both proofs and cryptography in a very elegant way. His interests cover things from networking, systems, and security. And so naturally, he's worked on topics that include untrusted networking, untrusted storage, and security against denial of service attacks. He's also won numerous awards, including the NSF Career Award, a Sloan Research Fellowship, an Air Force Young Investigator Award, as well as multiple teaching awards from the University of Texas. Now, from these introductions, you might have noticed that there's a correlation between working in verifiable computation and being named Michael. But it turns out there's an even stronger correlation in that all three of us did our undergraduate work at Harvard College, where the school motto of Veritas appears to have had some effect. So without further ado, let's turn to the topic of outsourcing computation. In particular, we're going to look at a scientist named Alice who hasn't had so much luck with her grants lately. And so instead of doing the computation locally, she's going to outsource some very important computation to the cloud. And based on the results she gets back from that, she might do some further thinking and run the computation again with some new data, hoping to get a different answer. But unfortunately, she gets the same answer back. And of course, eventually, it might occur to Alice to wonder, is the cloud doing the computation that she asked it to, or is it doing something a little simpler and probably cheaper from the cloud's perspective? Now, this seems like kind of a contrived example, but if you look at the customer agreement that you sign when you sign up with Amazon's Web Services or with Azure's for that matter, you see that there's basically no guarantee that you'll get anything back, or that the things that you get back have any correctness or good properties associated with them. And of course, it's not just scientists that are outsourcing computation. Today, it's fairly typical to take some task that would be too power intensive to run locally and outsource that to the cloud. And it might be nice to know that the results coming back from that are, in fact, correct. And even from the perspective of legitimate providers, who we like to think are not trying to actively change the results they're giving you, having verifiable results can help encourage confidence in the cloud and hence move more customers to the cloud platform. It may also command a premium over those services that don't offer this kind of guarantee. And we can look at it as a way of shedding liability, in the sense that if the customer is unhappy with the results they get back, the provider can prove to them that the results that they get back came from the inputs and the computation that the client specified and are not the result of mistakes or other changes that the provider might have made. And so before going into the details of this area, I thought it would be nice to have a sense of just how quickly this area is changing. So starting about 5-6 years ago, the state of the art was something called probabilistically checkable proofs, or PCPs, which is elegant and beautiful theory, but if you apply it naively to a computation such as matrix multiplication, you find that the verification takes something like 72 trillion years. And that's pretty bad in general, but it's even worse when you consider that the base calculation only takes about 15 milliseconds. So nobody's going to outsource under this regime. Now, a few years ago, we developed a technique that was based purely on cryptography and not on PCPs, and we're able to reduce these costs by approximately 10 orders of magnitude. Now, in many areas of computer science, if you do that, you're done. You just walk away, no more work to be done. But unfortunately, we were still left at about 37 centuries of verification time, so still plenty of room for improvement. Mike Wallfish's group has recently started work on improving the PCP-based line of work, so taking that original system and reducing, compared to the crypto system, by 6 orders of magnitude, and by the original system by over 16 orders of magnitude. Furthermore, you can take this and improve it even further by batching. So if you're doing a whole lot of computations all at once, you can reduce this verification load below the point at which it's to the point where it's cheaper than doing it locally. And so you can actually win here. Unfortunately, with these early systems, you often require a large batch size. So you need hundreds of thousands or millions of instances to make this worthwhile. Fortunately, as Mike will tell you during his talk, they've continued to do work along these lines and reduce this significantly to the point where it actually makes sense in a cloud computing setting. And then our work, we continue to work on the cryptographic side of things and reduce another 7 orders of magnitude on the individual instance verification to the point where we're actually beating local computation for individual verifications. And I think the most exciting part here is not the individual bars or the milestones along the way, but the fact that overall the costs in this area have fallen by over 23 orders of magnitude in the last 6 years. And we've seen similar improvements on the worker side as well, where the costs initially were just exorbitant. You could never even produce the proof in the first place, to the point where it's starting to look much more reasonable. Still costly, so it's going to cost you more to generate this proof. But if you're in a cloud computing regime where you might actually have extra resources sitting around, then maybe it's not too crazy to spend extra resources to provide this extra guarantee to your customers. And again, here we've seen 18 orders of magnitude fall. And in fact, we've also started combining some of our efforts. So Mike and I recently collaborated on a paper where we were able to reduce the overhead on the approver even more while still staying in the batching regime for the verification. So to talk about these systems a little bit more qualitatively, the early systems were based on something called fully homomorphic encryption, which is a very recent innovation and has the nice property of providing privacy of all of the individual inputs and the computations that you're working on. Unfortunately, the cost of that encryption is so high that those systems just aren't practical yet. The PCP line of work doesn't provide privacy, but can achieve very good efficiency when you can batch lots of computations together. And it also is nice in general purpose and makes the simplest cryptographic assumptions of all the current systems out there. The interactive proof system that Professor Mitzemacher will tell you about has even better practical performance, but gives up on generality for some computations, though recently they've started increasing the class of general computations they can handle. But for things like matrix multiplication, we can't even show that on the graph that I just showed you because they've gotten the performance so good for those specialized computations. We also did some work last year on, again, looking at other cryptographic techniques we might use, using something called ABE, or attribute-based encryption, which is much more efficient than FHE, and gives you nice properties like security against quantum cryptography or quantum computers, and allows you to do public verification. But unfortunately, the parameters are such that they just, again, not that practical yet. And finally, in some recent work, we were able to achieve practical efficiency using cryptographic techniques, which gives us this public verification property and allows us to do other fancy cryptographic techniques like zero-knowledge proofs. And so just to step back for a moment and say, well, really, how do we formalize this notion of verifiable computation? You can think of it in terms of 3 algorithms that we're going to run. The first algorithm is a key generation algorithm, which takes in a function, which you can think of as the program that describes what it is you want to outsource to the cloud. And it generates some key material. So in this case, say a public evaluation key describing the computation, and a public verification key describing how you're going to check the results. Once you've done that, you can outsource your inputs to the cloud, and the cloud can do the computation as it normally would. But this time, it's going to run a second algorithm called prove that takes in that evaluation key and outputs a proof that this particular output corresponds to this particular input on this computation. It can return that proof back to the Alice, and Alice can run the third algorithm, which is verify, using that verification key that she produced earlier. And that's going to tell her if the cloud is cheated or if the result is good. And of course, the key challenge here is to make sure that that checking work is less than doing the computation herself, or there wasn't much point to outsourcing in the first place. Now, you might want so this is kind of the basic setting, but you might want something more general. For example, you might want what we think of as a signature of computation. And since any other party can come along and say, hey, I have a computation I want to do as well, and he can receive a proof, he can check that proof using the verify algorithm, and he can decide whether he got a good result. Furthermore, he can show this proof to Alice, and she can independently verify that result as well. So she doesn't have to worry about the fact that Bob had access to this key, possibly allowing him to cheat her. So it really behaves like a signature for a message, but now we're signing entire computations. And so in the rest of the talk, I'm going to focus on my work on the cryptographic side of things. And then later we'll hear about the various techniques that my co-panelists have developed for avoiding cryptography, or at least minimizing the amount of cryptography you have to use. And so my portion of the work was joint work with some folks here at Microsoft, as well as some folks at IBM Research. And so the main thing that we contributed here was to develop a new protocol for general purpose, publicly verifiable computation. And it also happens to support what are called zero-knowledge arguments. And I'll get into a little bit more detail what that means in a bit. And we were able to do this by coming up with a new encoding that we call Quadratic Programs, that is a new encoding of computations that really lends itself to this type of cryptographic application. And the nice thing is that it gives us extremely good asymptotics. So the amount of work to set up that key in the first place is proportional linearly to the amount of work you would have done to do a single computation in the first place. The worker does quasi-linear work in what he would have done anyway to evaluate that computation. The verification depends only on the size of the inputs and the outputs, and not on the computation at all. And the signature is constant size. It depends only on the security parameter, no matter how big the inputs, no matter how complicated the computation.
What is n here?
You can think of n as the size of the original computation. So whenever a cryptographer shows you a bunch of asymptotics like this, you should always be a little suspicious about what's happening underneath the covers. For example, the early work on FHE had really good asymptotics, in fact, better asymptotics than this, and yet it's completely impractical to run in the real world. Fortunately, in terms of concrete performance, we did pretty well on this front as well. So we improved on the verification by 60 to 100 times. We improved on the verification by 7 orders of magnitude. And that signature really is small. It's about 288 bytes, about what you'd expect for an RSA signature. And so this gave us one of the first verification systems where we could actually beat native C execution on a per instance basis. And so in the rest of the talk, I'll tell you a little bit about how we were able to do this by walking through the pipeline of computation. So we start from a program written in a subset of the C language. We compile that to an intermediate language that's based on a circuit representation. We compile those circuits into what we call a quadratic program. And then we compile that program into those cryptographic protocols that I mentioned earlier. So in the first step, we need to do this compilation of C. And to do that, we wrote a compiler that understands a large subset of C. So it knows about variables, function calls. It knows about type defs, all kinds of compiler preprocessing languages. And essentially, it's going to take all of that and turn it into one giant expression. So it's going to unroll all of the loops. It's going to inline all of the functions and turn that into a giant expression similar to the secure multi-party computation literature, if you're familiar with that work. And so at the end of the day, we're going to convert that into an arithmetic circuit. So you can think of that similar to a normal circuit, but rather than taking bits on the wires, it's going to take large values, say integers mod some large prime p, and it's going to do basic operations that consist of adding and multiplying those numbers modulo that prime. We also developed some custom gates that allow you to test for things like, do I have a value that equals 0, which can be useful for doing loops, and we have a gate that splits a value into its constituent bits. And so that allows you to do sort of bitwise operations like XOR, bitwise AND, bitwise OR, and so that broadens the space of computations that we can cover. So once we've represented the computation as this circuit, we then need to convert it into a form that's more amenable to cryptographic verification. And so that's going to be these quadratic programs. And so you can think of the quadratic program as an efficient encoding of the original computation. And when I say efficient, what I mean is that we can take any original circuit, an arithmetic circuit in this case, convert it into an equivalently sized quadratic program that computes the same function. And so what that means is that we can take any polynomial time computation, or even any NP computation that can be verified in polynomial time, and verify that using a quadratic program. And we have a similar theorem that takes Boolean circuits and converts it into a related idea, which is called quadratic span programs. In this talk, I'll focus on quadratic arithmetic programs and try and give you at least some flavor as to how this might work. In particular, if you look at this example circuit we have here, it's a very basic circuit. It takes 4 inputs, produces 1 output. And you can think of it as sort of combining a series of very small equations for each of those multiplication gates. So in particular, that first multiplication gate says that C3 times C4 should be equal to C5. Similarly, the next multiplication gate says that if you add C1 plus C2, multiply it by C5, you should get C6, and so on for the entire circuit. And so at a high level, we're going to construct a pair of polynomials, D and P, that are going to encode these gate relationships in a particular fashion, such that if you evaluate the circuit correctly and wind up with a correct set of C values, then the D polynomial will divide the P polynomial. So what does that mean? Well, it just means that there exists some polynomial H such that we can multiply H and D and get back to P. Or to put it yet another way, it means that anywhere that D becomes 0 it must be the case that p becomes 0. And so by constructing these polynomials cleverly, we'll ensure that this condition only holds if you do the circuit evaluation correctly. And then inside of the cryptographic protocol, what we're going to do is check that divisibility property at a random point. And with high probability, if you've done it correctly and the divisibility holds, then the divisibility will hold at that random point. And if you've done it incorrectly, then the divisibility will not hold. So let's take one step deeper and look at how we actually do this construction. So again, looking at this example circuit, we're going to pick a root value, so an arbitrary value from the field, to represent each of these multiplication gates. So in this case, there's 2 multiplication gates, so we end up with R5 and R6. We're going to define the divisibility polynomial, d, to simply be the polynomial that becomes 0 at both of those points. So z minus R5, z minus R6. And then we're going to define the p polynomial that needs to be divided by d in terms of 3 sets of polynomials, v, w, and y. And in particular, we're going to create a v polynomial for each of the original inputs and each of the outputs of a multiplication gate in the circuit. So we wind up with 4 for the inputs and 2 for the multiplication gates. And we're going to define these polynomials in terms of the values they take on at these root values that we chose initially, so R5 and R6. And we're going to do so based on the left inputs to all of the multiplication gates in the circuit. So for example, we look at the first multiplication gate and we see that its left input is C3. So what that means is we're going to put a 1 for V3 and 0 for everything else, because nothing else is a left input to this particular gate. Then we're going to look at the left input to the second multiplication gate. Here we see that 2 inputs, C1 and C2, both feed into the left input of this gate. And so we're going to set V1 and V2 to be 1 and everything else to be 0. Fine? We're going to do the same thing for the W's. But the W's are going to represent right inputs to these multiplication gates. So we look at the first gate. We see that C4 is the only one feeding into the right-hand side. And so W4 is the only one that takes on a 1. Everything else is 0. And similarly for the second one, C5 is the only one going in. So W5 is the only one that's a 1. And finally, as you may have guessed, the Y's are going to represent outputs. So the first one, we look at the output. It's obviously just 1. It's C5, so Y5 gets a 1. And the second multiplication, C6, is an output. So again, Y6 is the one getting a 1. OK, so if you've stuck with me this far, I now need to convince you why this makes sense. Why is this useful? Well, remember, we're going to define, or in particular, we're going to define this polynomial to be the sum of all of the wire inputs applied to the V's times all of the wire inputs applied to the W's, and we're going to subtract off the Y's, which looks like kind of a hairy equation. But remember, our condition here is that we need d to divide p. And in particular, that means anytime d becomes 0, we need p to become 0. And we define d to be 0 at both R5 and R6. So that means that we need to look at what happens to p at R5. Well, if we look at the first term, we see that all of the v's are going to be 0 at R5, except for v3, which is going to become 1. So that entire summation over the v's is going to boil down to just be the term c3. Similarly, for the w's, we see that all of them are 0, except at w4. And so that entire summation is going to boil down to being just c4. And similarly for the y's, everything's going to go to 0, except for y5. And so we're going to wind up with c5. And so what does it mean for p to be 0 at R5? It just means that C3 times C4 has to equal C5. And that's exactly the equation that first multiplication gate is meant to encode. And we see the same thing happens at R6. If we evaluate p at R6, we see that the v's boil down to be just C1 plus C2, the w's boil down to be C5, and the y's boil down to be C6. And so again, for p to be 0, it means that C1 plus C2 times C5 has to equal C6. And again, we've just checked that multiplication gate. So essentially, by checking this divisibility property, we're checking all those individual equations in one fell swoop. So now that we've built up all these polynomials, we have to turn that into a cryptographic protocol. And in particular, I'm not going to go into much detail here, but the high-level intuition is that Alice is going to generate all of those polynomials. She's going to pick a random point s, and then she's going to evaluate all those polynomials at that secret point and stick it up in the exponent so that it's hard for the worker to see what value she chose. And she's going to send that over to the worker, who's going to evaluate the circuit just like he normally would. And that's going to tell him all of those C values that he needs to know. He's going to apply those linear combinations up in the exponent of the group to compute those summations, but he won't actually know the values of the underlying polynomials. And finally, he's going to solve for that extra polynomial h that proves that divisibility holds, and he's going to stick that up in the exponent as well. So finally, he's going to end up with a few terms that he's going to return back to the verifier. And the verifier is essentially going to do that multiplication up in the exponent using a cryptographic tool called a pairing that lets her get away with that once. And so at a very high level, we're just checking divisibility. And if that divisibility holds, then the verifier will know that the computation was done correctly. Now we can take it another step and add some more fanciness on it to make it zero knowledge. So why would you care about zero knowledge? Well, there's a movement afoot to add smart meters to people's houses so that the meter will send how much electricity you're using back to the electric company at a very fine granularity. So they can bill you more during the day and less during the evening, or bill you more when other people are using electricity and less when other people aren't. So this is great from a resource allocation standpoint, but it might reveal some information that you're not comfortable sharing with the world. And so we can use zero knowledge techniques to help prevent this kind of scenario. In particular, we can have the smart meter output the results to Alice directly rather than to the billing company. And the billing company can provide the billing function directly to Alice along with one of these evaluation keys. Alice then can decide how much she owes by evaluating this function on her inputs, and she can generate a proof that she's done this evaluation correctly. The zero knowledge aspect is that she can then re-randomize that proof such that when she sends the result back, the billing company can tell that she did the computation correctly, but learns nothing about the individual inputs. And so both parties get what they want out of this computation, and so we're living in a better world. And the nice thing is, I'm not going to go into how this works, but it only adds about less than 0.1% to the overall protocol overhead. And so it comes essentially for free on top of our existing protocol. So I'll talk very briefly about the implementation. We've implemented 6 or 7 sample applications, things like matrix multiplication or a lattice gas simulator to say how gas molecules are behaving. We've implemented a compiler that takes that into circuits and another compiler that takes that into the cryptographic protocols. The protocols themselves operate over BN elliptic curves, if you're interested in that. They provide about 128 bits of security. The entire system is single-threaded, but Mike's group and Michael's group have both done some work on parallelization, and I think our system would be equally amenable to that. And the source code for this is available, so if you want to try it out, you can play with it on your own system. The key takeaway for the evaluation is to look at, are we beating native execution? So you can see on the x-axis how long it would take if you compiled that C program directly and ran it on your own computer, versus on the y-axis how much it costs to verify the results that come back. And so you can see for 3 of our applications, we're actually, for large enough parameters, so large enough matrices or running the simulation long enough, we're starting to cross that threshold where you're actually beating local execution. So you're better off verifying the cloud computation than doing it yourself. Now, it's a little hard to see, but there's 3 applications that are kind of stuck over on the y-axis. If we zoom in, we can see that they're all trending in the right direction. So if we push them far enough, we'd eventually cross that y equals x line. Unfortunately, these applications don't translate as well into the circuit representation, and so we pay more to compute them, and so we can't push the application parameters quite as large on the laptop where we were running these experiments. And so just to go into a little bit more detail, for 2 applications, in this case, evaluating a polynomial and simulating gas particles. When we translate that into a circuit, you get about 800,000 arithmetic gates. That translates into a few 100,000 polynomials. Those are used to generate the keys, which takes a minute or 2, which is not too crazy. The verification key, which you might put on your phone to verify the results, is typically about 1 kilobyte. The evaluation key, which you would upload to the cloud, is larger, a few 100 megabytes. And the time to generate the proof is reasonable, but not as low as we would like. There's still a fair bit of room for improvement here. Fortunately, when you finish this computation, you wind up with a proof that's only 288 bytes, regardless of the computation, so the network overhead for sending that back is very low. And of course, the verification takes on the order of 10 milliseconds, which compares quite favorably for native execution for the polynomial evaluation, not so favorably for the gas simulator, like we saw on the previous graph. And that's, again, because of the translation to the circuit model. So you can see here that translating to a circuit, it takes about 20 times as long for the circuit on the polynomial as it did for the native. But for the gas simulator, it takes over 400 times as much. That's just because of the inefficiency of the translation. So in future work, obviously, a big step that we're working on now is ways in which to move beyond the circuit model so we can avoid some of those inefficiencies. Ways to do more efficient computations over signed data to support scenarios like the smart meter that we talked about. And of course, additional applications of this quadratic program, since it seems like a very nice encoding and we think it can be applied to other areas. And so just to quickly summarize my portion of the talk, we've developed this encoding for computations that seems to lend itself very well to both verifiable computation, zero-knowledge programs, and possibly even things like attribute-based encryption. We've built a tool called Pinocchio that compiles C programs all the way into verifiable computation protocols, and that gave us orders of magnitude of improvement and gave us one of the first systems where we were beating native execution on a per-instance basis. So with that, I'd like to thank you for all of your attention. And we have time for 1 or 2 questions, and then we'll save all the rest of the questions for the end when you can have at all 3 of us. So any quick questions?
So when you talk about the verification time, it's only after receiving the proof, right?
Yes.
Do you consider like the total computation time from the moment the time starts?
No. No, at the moment we aren't counting that, in part because the prover cost is so expensive. So in theory, you can bring that down. In fact, both of these gentlemen have shown that you can bring that down by parallelizing the effort. So that improves latency. So in theory, you could, if you threw enough machines at it, you could bring the latency down significantly, and then maybe it would make sense to count the total time. At the moment, though, well, first, you're still paying for all that computation, even if you're throwing a lot of machines at it. And second, you still have the issue of uploading it to the cloud and then getting the results back. So I think at the moment, it's best suited for things where it's just computationally or maybe power inefficient to run on your local device, and so it still makes sense to do this outsourcing, even though you might have to spend longer waiting for the result to come back.
So among the programs you mentioned, for example, the text multiplication,
Yep.
some of these can be done with cheaper fully homomorphic encryption schemes. And so would you consider that, let's say I have a BGN scheme, wouldn't it be better that if I use the older schemes that you had in the 2010 paper, how would you compare with that? I know it's much slower if you use a fully homomorphic scheme.
Okay. Yeah, so you're asking, could we take advantage of the improvements in homomorphic encryption to do better for some of these particular applications? It's a really good question. I think it would still be more efficient to use one of the existing verifiable computation systems than to use that, just because you'd be paying a lot for that extra hiding. Now, for applications where you care about the privacy, then sure, you should definitely look into that. But I still suspect that fundamentally, anytime you're adding that privacy layer, you're going to be losing something in the efficiency. So I think we should probably cut it off there and let Professor Mitsumacher take over.
Thanks. I'm Michael Mitsumacher. I'm going to be presenting really the work of my student Justin Thaler, who is just about to turn in his thesis, and I should point out will be on the job market next year. As we've already heard from the beginning, but just a quick review, there are certain goals for verifiable computation. You want to offload your stuff to the cloud, but have some sort of correctness guarantee when it comes back. Maybe this isn't because you assume the cloud is malicious, but there could be bugs or other sorts of smaller problems. So you want something that will work against malicious clouds, but also lightweight enough for benign settings. You want to make things hopefully faster for the verifier, but also minimize the effort required for the cloud to produce this correctness guarantee. One of the ways that our work is a bit different than the other pieces of work is that we want ours to work, or ours was designed to work in a streaming setting. So ideally, the user won't even have to maintain a local copy of the data. And I'll discuss more about the streaming model as I go. Okay? So as Brian pointed out, we started from the realm of interactive proofs, right, where you have you on your little laptop and a much bigger cloud provider who can do the work for you. So you send over your data to the cloud provider. And again, in our model, you may not even have to keep the data after you send it. You may just keep some fingerprint of it, as I'll describe later. And in the interactive proof model, then after they do the computation, you sort of challenge them and say, hey, okay, well, if you did the computation correctly, you should be able to answer this question. And you get back an answer. And after the question and answer, you send these sort of challenges, responses. Can you challenge, response, challenge, response. And this may go over some number of rounds. You might have sort of a back and forth conversation. But eventually, you become convinced that they did the computation correctly. And you'll decide to hopefully accept because they've answered your challenges in the way that you would have expected. Okay, so this is a conversation-based approach. Although in some cases, you can develop one-round versions where it doesn't even have to be a conversation for certain problems. Okay. All right, so modeling this in the theoretical way we talk about this, we have a prover P and a verifier V. The prover solves the problem and then just tells you the answer. You have a conversation, and the goal for the prover is to convince the verifier that the answer is correct. The sort of properties we want in the theoretical sense are completeness, that if you have an honest prover, it will always convince to accept, and soundness, that a verifier will catch a lying prover with high probability. Okay. Now, interactive proofs have been around for a long time. They're nothing new to complexity theory. We didn't invent interactive proofs by any means. They've been part of some of the great seminal results in theoretical computer science, from IP equals P space, zero knowledge proofs, PCP theorems. But they've actually, up to this point, had little impact in the sort of delegation of computation scenarios. And our claim was that, we went into this thinking, well, why is this the case? How can we make these more practical? Because certainly there seem to be applications. And if you look at the original theoretical work, it was really trying to deal with the situation where you had a set of hard problems. Like it was saying, oh, well, suppose you had a prover that could solve NP-complete problems or sharp P-complete problems. And of course, we don't actually have provers that do that. And in practical scenarios, that may not be the real situation where we actually want to offload this sort of computation. But in 2008, there was a paper, key paper that we rely on quite a bit for our work by Goldwasser, Kalai, and Rothblum, labeled Interactive Proofs for Muggles, and hence some of the Harry Potter pictures you're seeing. And the goal here was to allow the verifier to try and run quickly so that you could outsource for useful, easy type problems, not necessarily NP-complete type problems. And also that the prover did not need a whole lot more time to prove correctness than to actually solve the problem. Okay. Now, why is it that this result didn't immediately yield an out-of-the-box solution? Well, it's because, to a theorist, not a whole lot of extra time for the original paper meant a cubic blow up in essentially the computation time, the size of the circuit, which was a bit difficult. And also in the original version, the verifier had to have the full input. So one of the ways that we've been pushing on this is to actually say, okay, you don't actually need to keep the whole input. We can have this work in the streaming setting as well. So the idea is that the data itself, you're working with a big data set. That's why you're offloading the computation. You don't actually have to store the data. You have to see the data so that you can keep some sort of fingerprint, do some sort of processing that you'll use later in these challenge response scenarios. But you don't actually have to keep the data itself. Okay, so you can look at the data in a one-pass streaming manner. Our claim is that this is a very useful sort of property to have in the context of dealing with these big data computations that you want to offload to the cloud. Okay, so again, just a reminder, many of you will have seen this before. In the data stream model, we think of having elements swim by from some sort of universe, and you see them sort of one at a time. And your goal as you see them is you compute, at the end of the day, you're trying to compute some sort of function on this stream, but the actual verifier isn't necessarily going to keep the whole stream. They're going to work with an amount of memory that's sublinear in the actual size of the stream and the size of the universe. And they're just going to see the data as it comes to them and have to deal with it and then move on. Okay, and the results that we give actually work in this setting. Okay. We have results for different settings, for different sorts of problems. Model where you have one message, sort of the non-interactive. The prover just sends the verifier, say, an email with the answer and a proof attached. The cost of having less interaction of sending it this way is that you actually, of course, have to have a sort of a larger bit of data to send. What I'll be talking about more in this talk is the case where we actually do the multiple rounds of interaction and you have that conversation. Some of the costs that should be considered, or our main cost that we consider, is going to be the amount of communication that actually takes place and the amount of memory that V needs to keep as seeing the data stream. There are other important costs too, such as the actual running times and the number of messages that I'll be talking about. So again, this is Justin's thesis work. He's been working on this with other people, myself included, for a long period of time. And there's sort of two prongs. I'll be talking more about the first prong, or the first prong is really what we're talking about here in this panel, which is to do general purpose implementation. You're trying to verify, essentially arbitrary computations. Okay? And there we're going to build on that GKR protocol I talked about. But he's also done a lot of work on developing highly optimized protocols for very specific problems. And the goal here would be that if we could develop a rich enough class of building blocks with very efficient implementations, then you may want to cast your computation into those sorts of computations. And by working with very specific computations, you can potentially get much, much more efficient sorts of schemes than working in the general purpose model. So in particular, I'm going to look at sort of a specific example of one of these sorts of second prong type approaches, just to give an idea, because it sets up a lot of the technology that we actually use in both settings. Okay? As Brian talked about, one of the key ideas is this notion of arithmetization, right? So instead of thinking of things as being over just the 0-1 binary alphabet, you sort of work with, you arithmetize by changing things into addition and multiplication. And one way to think of that is that you're going to be working, now with polynomials, again, sort of a way that Brian described, and you can work with them over a larger field. You don't have to be thinking in terms of just zeros and ones. You can be thinking of numbers, even though you know the actual inputs to your circuit are going to be zeros and ones. And a trick here is when you're dealing with this sort of way of thinking about for polynomials, is to view what we call low degree extension, right? So you look at this polynomial and you say it's defined over a field. You know how it has to behave in binary, but you can use the fact that you're working over a larger space of numbers. All right, so here's an example problem that lets you see the power of this sorts of technique. Okay, so the second frequency moment says you're going to be seeing letters in an alphabet go by in a stream. What you want to do is keep track of the squares of the frequencies of these items. Okay, so you can see this sort of example here at the bottom, A, B, A, C, B, A. You've seen A 3 times, B twice, C once. So the second moment here would be 14, because it's 3 squared plus 2 squared plus 1 squared. There's an associated frequency vector, and you can think of the frequency vector sort of being the representation that we're going to end up using after the stream goes by. Okay. So what we have for this scheme is something that uses square root of n amount of communication and square root of n space. So even if you have terabytes worth of data going by, you've turned this down into a few megabytes of space and communication. And this is essentially tight. There's a lower bound on the product of the communication and space required. Okay. So what's the sort of trick that we use for this? Okay, we're trying to come up with the sum of the squares for this frequency vector. So we can think of this frequency vector, we'll split it up into the sort of frequency square, right? If there are n elements we're trying to keep track of, we'll break it up into a square root of n by square root of n square. Okay. All right, and then the prover is going to do all these calculations to figure out the second frequency moment. And we'll just send the answer in pieces. Instead of sending us a single number, it'll send us square root of n different numbers. Okay, one for each row in this square. And what the verifier can do to try and check that the calculation is being done correctly is pick a row at random and check that the prover is lying. Okay? And if the prover is lying, then there's a chance of being caught. In fact, a 1 over square root of n chance of being caught. So the verifier only requires sublinear amount of space, square root of n amount of space, and a chance of probability of 1 over square root of n. Well, that's not a very good probability of catching that a problem has occurred. So we need to be able to beef that up. So what we'd like is a setting that says, well, wait, even if the prover lies even about just one thing going on, they'll have to lie about many of the pieces going on. And the idea is by phrasing this in terms of these low-degree extensions, we can essentially build an error-correcting code on top of this actual input. Okay? Right, so we think of these values as being on a polynomial, and the point is that we have this frequency square, and now the verifier can pick a random row, and the point is that if the prover tries to lie, the prover is going to have to lie on most of the actual things, and so we'll be able to use this to catch these sorts of problems with high probability. All right, so here's just some sort of experimental results with one round versus multi-round. Essentially what we see is that there was room for improvement even in the one-round scheme using efficient fast Fourier transforms, and the multi-round schemes are even more efficient. They all sort of are linear on this log-log scale, but we're getting to actual efficient times with very large runnings, very large problems. All right, so now let me say, now that you have this sort of idea, how do we think of this for general purpose IPs? Okay, so now the point is that, as Brian pointed out, we're working over circuits, right? This is what an F2 circuit would look like. We have the frequency vector as input. We sort of square each of these values and then sum them up. Okay, so the prover starts by saying, hey, here's the output. Here's the answer. Okay. And the verifier makes some sort of challenge. And the point of this challenge, the way you set up this challenge, is the prover has to respond with something that tells you about information about the circuit at the next level down. Okay? And then you can continue this process recursively. The challenges go back and forth. And the way you can think of each challenge response is saying, OK, you've committed to something about this level of the circuit. I'm going to force you now to commit to something about the next level down in the circuit. And eventually, the prover is going to get down to the inputs. And the inputs is what the verifier has actually seen and dealt with. Right? So the verifier, by performing proper sort of computations, fingerprints on the input, can check the prover statement. And I should point out that these fingerprints are not computation dependent. It doesn't depend on which actual circuit you're trying to verify. You can develop these fingerprints just from the beginning and then later decide what sort of computation you want to do on the data stream. Right? So this saves the verifier significant time and space. In particular, even when multiplying 512 by 512 matrices, we're already much faster than the verifier doing itself. Okay? And this will only get better as we deal with large input sizes. And we've done this in a way that minimizes the prover's overhead. Right? Theoretically, we brought the prover's runtime down from cubic in the size of the circuit to S log S, where S is the circuit size. And we've done a lot of additional engineering, things like picking the right finite fields to work for, using the right kind of circuits, and so on. Okay? I'll show some more results further. In fact, just recently, and this is work that will be appearing in Crypto shortly, was able to improve things for regular circuits, get things down to linear time. And you might think that the log S factor isn't so big, but we're talking about circuits, right? So these circuits are potentially millions of gates. So a log S factor actually is orders of magnitude. And in fact, Justin's been able to get programs that are less than 10 times slower than a C++ program for the prover. Right? It's obviously going to be faster for the verifier, but the point is that within a striking distance, within an order of magnitude, to actually develop the proof, then that takes the time for the prover to actually solve the problem. Right? So here are some sample applications, distinct, the number of distinct things. Matrix multiplication, maybe the key thing to note is the gap between the prover time, P time, and the circuit evaluation time. And again, you can see they're within an order of magnitude of each other. So you're not necessarily paying a whole lot, even on the prover side, to get this sort of verification. I can do 2 more minutes. Justin's also expanded this work to deal with irregular circuits by using the idea of data parallelism and subcomputations. The idea is if you have repeated subcomputations, you can actually set it up that you essentially just have to deal with that circuit once so that really the cost is from the size of the subcomputation, not from the size of the total circuits itself. And we've also done, as Brian pointed out, a great deal of work taking advantage of parallelism, and in particular in this area showing that we can deal with these sorts of data parallel type computations specifically. One of the last things in this paper that's just coming out is Justin has specifically a very good result for matrix multiplication. Again, looking back, he was able to take this general work, use it to look back at a specific problem, and come up with a new matrix multiplication protocol that takes essentially no additional time and space over just regular matrix multiplication, that it sort of ends up being in lower order terms. And we think this will be a great primitive for other sorts of routines in this space. All right, so future directions, we'd really like to avoid the circuit model, which is what we use and what we've depended on for this work. We'd like this to work for more general classes of C programs. There's certainly more room to continue pushing the speed and functionality of these sorts of systems. Another sort of way of thinking about this is we've been talking about this in terms of big data and big data cloud problems. But another way of thinking about it is actually going to the very small, right? So you think you have your computer, but you might want to put in some sort of high-speed attachable device. Maybe you have a GPU that you just plug in that handles certain specific computations, and you'd like it to not only do that computation, but to prove to your main home trusted machine that it's actually done it correctly, right? That when you bought this special piece of hardware, that it's actually doing the job that you decided to offload to it. And so these are some of the things that we're looking at in terms of future directions. So thank you.
I think we have time for one quick question while Mike sets up.
So I'm trying to understand this streaming setting. Are you kind of implicitly assuming it's verifiability because in the sense that the verifier is not the data owner?
Sorry, could you repeat it? So I didn't get the question.
So, like, are we implicitly assuming, let's say, the verifier is not the data owner, so it's like a public verifiability setting here?
No,
Is there a requirement that the
what
verifier doesn't store?
Well, what we're saying is that the data is so big. I mean, if you look at a lot of the applications of the cloud, you have these like giant astronomy data sets or giant retail transaction data sets or stock data sets, where the point is that these things are so big that you're not actually storing them, say, on your laptop, that you're offloading the data to the cloud to begin with. So there's already some notion of trust in the sense that you're trusting the cloud to hold your data. Now you're extending that notion of trust. So you're saying, OK, not only am I going to have you hold the data, but because it's so big, it's not even clear I can download it back to myself to compute on it. I'm going to allow you to compute on the data as well. But I'd like to be able to trust not only that you're holding the data correctly, but that you're doing the computations correctly. So it's not saying that this is public information or anything like that. It's just saying that we have the potential to deal with data sets that are so large that we're not even holding the data ourselves, but we're offloading that aspect as sort of a priori, and now we're trying to extend that.
Okay, so you can save the rest of the questions for after our final speaker.
Okay, is this thing on?
Yeah.
Brighton, can you hear me? Okay, awesome. So thank you, and Brian, thanks for the invitation to speak here. I'm going to be talking about some of the work that my group has done in this area over the last few years, and also present a framework for organizing this work and some of the challenges. This work is collaborative with folks at UT and outside. I want to recognize my senior student, Srinath Sethi, who's driving the project, and my faculty colleague, Andrew Blumberg, who's here. Raise your hand. Okay, so you've heard the problem set up in the excellent talks of Brian and Michael, but I just want to emphasize how exciting all of this is from a systems perspective. When my collaborators and I started working in this area, no one had implemented any of the theory. And in fact, my systems colleagues thought that I was crazy for spending time and graduate student cycles on this. Since then, though, there's been a lot of activity resulting in a rich design space of works that can properly be labeled systems. To organize this design space, I find the following framework helpful. It's organized around a trade-off between performance and expressiveness. Vertically, we have qualitative costs, mainly for the verifier. Horizontally, we have the class of computations that the systems apply to. Higher means lower cost. Rightward means more expressive, so higher and to the right is better. I'm going to slot a system in here if and only if it is implemented with published experimental results. So the first two systems in the area were CMT, which you heard about in Michael's talk, and Pepper, in which my collaborators and I refined an efficient argument system, a kind of interactive protocol. And Pepper was in principle general purpose, but it only achieved reasonable performance for a restricted class of computations. We followed Pepper with Ginger, which expanded the applicability of Pepper, but the situation there was similar as far as performance. Reasonable performance for a restricted set of computations, ridiculous performance on the order that Brian mentioned for computations outside that set. We followed Ginger with Zatar, which expanded the reasonable performance to a much larger set of computations. Zatar derives a lot of its power from the beautiful quadratic arithmetic programs formalism that Brian mentioned of Gennaro, Gentry, Parno, and Raykova. The next publication was Pinocchio, which also uses that same formalism, but in a way that achieves more cryptographic properties in exchange for higher expense. We were able to fill in the gap in the frontier line between CMT and Zatar with our work on Allspice, which achieved very good performance, but at the cost of an inexpensive setup phase. Following Allspice, Justin Thaler borrowed some of its techniques, introduced a raft of other ones, and produced that excellent performance that Michael described. This is the best performing system in the literature, although its applicability, of course, is restricted. At this point, none of the depicted systems can handle computations that have side effects. They can't handle storage. They can't handle state. We have been able to remove that restriction in work that will be appearing at SOSP in a few months. Pantry extends the verification machinery to handle things like verifying queries on remote databases, verifying MapReduce computations, verifying computations that use indirect memory references. Prior to Pantry, pointer values had to be known at compile time. Speaking of compilers, all of the shaded systems ship with compilers. Brian gave an excellent example of what those pipelines generally look like in these systems. One important axis that the framework here doesn't capture is cryptographic properties. The systems in the bottom row achieve things like zero knowledge, non-interactivity, meaning that their setup costs can be amortized indefinitely. I should say that the way that Pantry achieves these cryptographic properties is by leveraging Pinocchio, which it can do because Pantry applies to a number of the systems in the literature. To put all of this in context, Brian talked about Pinocchio. Michael talked about the systems in the upper left. The rest of my talk will be in two parts. In the first part, I'll do a quick performance study of the shaded systems so you can see what the issues are in the area. We handle integrity, not availability in this research area. And then in the second part of the talk, I'll describe our work on Pantry, which I'm very excited about, which concerns extending the verification machinery to real computations that people use the cloud for. Now, in doing this performance study, there's three questions we need to ask. The first is, what is the verifier's per instance, that is per input-output pair cost of doing a verification, and how does that compare to simply executing the computation locally? Second, what is the verifier's costs, or what are the verifier's costs from participating in the protocol in the first place? And third, what are the workers' overheads? And in doing this performance study, I have a few ground rules. The first is that I'm going to include a system if and only if it's implemented with published experimental results. The second is that the data here is going to be from all of our re-implementations of all of the systems that appear. I insist that my graduate students recover performance as good as or better than what's reported in the original papers. We're, of course, going to run these experiments on the same systems. Turns out there's not a lot of experimental variation, so I'll just report the averages from 3 runs. I should say that for a few of the systems, namely those whose experiments don't terminate in our lifetimes, we're going to extrapolate from detailed micro-benchmarks. We're going to measure 2 classes of systems, the general purpose ones and the special purpose ones. And I should say a little bit about the general purpose ones. Brian gave an excellent presentation of Pinocchio. The line of works from my group, Pepper, Ginger, Zatar, is best explained by comparison with Pinocchio. So in Pinocchio, well, let me just say notationally, what the superscripts represent are different instances of the same computation, different input-output pairs. And the rectangles denote the types of proofs that the worker sends to the verifier to convince the verifier that the worker computed correctly. Now, in the world of Pinocchio, the verifier can get back a verification or a proof after a given output is supplied by the worker to the verifier. Pinocchio has a setup cost that's per computation, and then that setup cost is amortized indefinitely over multiple instances of the same computation. In Pepper, Ginger, and Zatar, by contrast, verification can only happen, that's what these stacked rectangles denote, at the end of a batch, and that those costs are amortized only within the batch. So qualitatively speaking, Pinocchio's amortization behavior is superior, but of course we have to ask about the qualitative and relative costs of these two things. So returning to the setup here, I'm going to look at 2 benchmarks, matrix multiplication and a clustering algorithm. And so the first question concerns per instance verification costs. What we see here is that several of the systems on a per instance basis, I'm ignoring setup costs for a second, beat native execution. There's only 2 problems, though, or there are 2 problems with this graph. The first is that 50 milliseconds denoting the cost of local computation is quite optimistic. If you turn on the optimization flags on your compiler, it turns out that native execution is actually 5 milliseconds. And unfortunately, none of the systems are beating that. However, optimistic baselines, and I'm as guilty of this as anybody else, are endemic in our research area. So I'm just going to imagine that the baseline is 50 milliseconds. The second bummer, which is sort of, you can imagine that there's lots of page faults or something. But the second issue here is that none of this actually takes setup costs into account. And the question you have to answer in analyzing setup costs is, what's the crossover point? How many instances of a computation have to be outsourced before it's worthwhile to use the verification machinery versus computing locally? And to analyze that, I'm going to take each of those y values there, and those are going to be the slopes of the total cost lines that are depicted here. So the slope of the black line is the cost of computing locally. The slopes of the red lines are the y-axis values that we saw before, but this graph actually has the y-intercept representing the setup costs. And what this graph is showing is that some of the general purpose systems actually do have a crossover point that's reasonable, tens of thousands of computations. What this graph is not showing is that Pinocchio's amortization behavior is superior in that once Pinocchio passes that 50,000 mark, all of the other instances of that same computation are gravy, whereas for Zatar, it's only the instances within the batch that count as gravy. Zatar then has to incur that setup cost on the y-intercept for each batch. Now what I'm going to do is take each of those crossover points on the x-axis, put them on the y-axis, and compare them to the special purpose approaches. And this graph is showing you two things. First, if you're willing to use special purpose approaches, your crossover points are far superior. Second, the special purpose approaches don't always apply. But it is nice that something like Allspice or even CMT, as Michael said, one run of it is better than executing natively. The third question we have to answer concerns the workers' costs in all of these schemes. And unfortunately, what this graph is showing is that the workers' costs, or the prover, as Michael called it, is unfortunately orders of magnitude, 10 to the 4, 10 to the 5, et cetera, more than computing locally. I don't have Justin's most recent work on here because it came out too recently, but it looks like for some computations, he's going to be able to do way better than this. To quickly summarize the performance in this area, we've come a long way. None of the systems is at true practicality. The biggest disaster, of course, is the workers' costs. The verifier can get close to practicality either if we're willing to make assumptions about special purposeness or if there are multiple instances of the same computation to verify. Now, you might ask yourself, when are there tens of thousands of instances of a computation to verify? And when do we have an abundance of CPU cycles for the worker? And the answer is cloud computing. Data parallel cloud computations exactly match this requirement for a crossover point because they involve the same computation on different inputs. And with that, let me turn to the second part of this talk, which concerns broadening the expressiveness of the verification machinery in the context of our upcoming work on Pantry. And to motivate Pantry, let me just observe that prior to it, computations could not have side effects. All inputs had to travel from the verifier to the worker. All outputs had to travel back from the worker to the verifier. Now, matrix multiplication is an excellent example of this pattern, and it was an important test for our area. But if we want this area to truly succeed, we're going to have to handle real computations that people use the cloud for. Under Pantry, we can handle something like verifying queries on remote databases, assuming that the verifier starts with a digest of the database. Or we can handle outsourcing computations that work with indirect memory references. Prior to Pantry, pointer values had to be known at compile time, ruling out any notion of a RAM abstraction in the outsourced computation. Or the verifier can outsource a MapReduce computation, getting back an assurance that the named output files truly contain the data that is the correct data that would be output by the MapReduce computation. To explain how Pantry does this, I'm going to review the pipeline that Brian mentioned that these systems have. It starts with a high-level language, compiles down into a set of constraints on circuit execution, into a quadratic arithmetic program, into binaries that implement the verifier and the worker, at which point the worker can prove that it computed correctly to the verifier. The differences in the systems, Ginger, Zatar, Pinocchio, and so forth, concern the last stage of the pipeline, how this QAP encoding turns into a proof, what's in the binaries that implement the verifier and the worker. But I'm going to focus on the front end of the pipeline because that's where Pantry's innovations are. And And I'm going to explain this front end slightly differently from what you heard because it explains what's going on in Pantry. So one way to understand the front end of these pipelines is that they take as input a high-level language. For example, in a subset of C, Pinocchio, I should say, was the first to work with C in particular. They compile them down to a set of constraints on circuit execution, meaning a system of equations with a distinguished input variable x and a distinguished output variable y. And that system of equations is set up in such a way that when that input variable x takes on the value foo, the system of equations admits a solution if and only if the output variable y is equal to bar, where bar is the correct output of the computation applied to foo. As an example, the decrement by 3 computation is in the upper left of the slide. That's equivalent to the constraints in the upper right because, for example, if we take x and set it equal to 7, then the output variable, the system of equations is consistent if and only if the output variable is set to 4, which is exactly what we want since 4 is the correct output of this computation when its input is 7. Now, I should say, returning to the pipeline then, it decomposes into 2 phases. In the first phase of the pipeline, a high-level computation gets compiled into a set of constraints in such a way that correct program execution is tantamount to satisfiability of the constraints when the distinguished input variable x is bound to the verifier's desired input and the distinguished output variable is bound to the purported output y. In the second stage of the pipeline, the worker proves to the verifier that indeed it knows a satisfying assignment. How this is done is way outside the scope of this talk. The question I want to answer is, how can we leverage the second stage of this pipeline? And so our design question becomes, how can we encode the interaction with storage and constraints in such a way that correct interaction with storage is implied by the satisfiability of the constraints? And I'm going to answer that question by telling you about a very bad idea, an idea that we're not going to follow. So the bad idea would be to have one constraint variable for each cell of memory. We could then faithfully represent interactions with RAM or storage or state, like a load operation would be equal to those constraints that you see on the right. The problem is, for every single load operation, we now need 2 constraint variables and 1 constraint, which is a lot if you imagine 2 to the 32 cells of memory. So instead, we're going to turn to a different idea, and in order to explain that idea, I need to review the concept of self-certifying blocks from the world of untrusted storage. In that world, forget about Pantry for a second, and imagine that there's some storage server that a client doesn't trust. If the client starts with digests that it's presumed to have retrieved through trustworthy means, it sends those digests to the untrusted storage server, and then when the block travels back to the client can check that the blocks are correct because the block is expected, a hash of it is expected to equal the digest, and then the client performs that check. Self-certifying blocks are interesting for Pantry for 2 reasons. First, they remove the exponential association between the possible values in a memory store and the names of that store. Given a set of data, there's only one possible name for it, a collision-resistant hash of it. And second, existing work has shown how to use self-certifying blocks as a substrate for building higher-level abstractions like verifiable RAM or untrusted file systems. Note, though, that in this picture, the client is actually retrieving the blocks and handling them. What Pantry will do will be to represent the interaction, Pantry will represent just the checks of the blocks themselves in constraints without the verifier needing to handle the blocks. Turns out this can be done reasonably efficiently, and I should say that the high-level idea here was known in theory that this could be done. Pantry's contribution consists of demonstrating that, in fact, it can be done and of being the first to actually do it, which we do by extending the subset of C with 2 primitives, vget and vput. In a correct execution of the program, vget, which takes as input a digest, a hash of some data, must return a set of data such that the hash of that data is the input to vget. The situation with vput is similar. Using this primitive, then, we can implement a computation in the subset of C, extended, that expresses the notion of adding an input value x to a value that's referenced indirectly using the vget. It compiles, the thing on the left compiles to a set of constraints that express the hash function. And then the key point is that the only way to satisfy these constraints is if the worker chooses a value z such that the hash of z, in fact, equals the digest. This is equivalent to doing a verifiable load, at which point that value z is available to the rest of the computation. And I assert that the constraints on your right are equal to the program on the left. Putting the whole pipeline together, it looks like this. Recall that the second phase of the pipeline proves from worker to verifier that a satisfying assignment to the constraints is known. Meanwhile, the work of Pantry is to take the various cryptographic checks of this hash function, encapsulate them in vput and vget, and turn them into constraints. And finally, existing work, not ours, work with a long history, shows how correct interaction with storage can be represented as vput and vget. And if you compose those three things together, what you get is that if the verifier gets convinced by the worker that it knows a satisfying assignment, then the interaction by the worker with storage is correct. We're not out of the woods yet because we'd like to build higher level abstractions on top of vput and vget, things like RAM or search trees. Existing work shows how to do that, so I'm not going to take up too much time with it, except to say that you write your computation using actual interactions with RAM. That gets compiled into a subset of C that uses vput and vget, which gets compiled into constraints. I will take a minute to explain how we use MapReduce, or how MapReduce works in this context. So, in the world, MapReduce is going to use vput and vget as follows. The verifier is going to outsource a map function and a reduce function and supply a set of input digests to the MapReduce infrastructure. And what the verifier is going to be given back are a set of digests such that the data that is the correct output of the MapReduce function better have as its hash these digests. The cool thing about this is that the verifier can then take those output digests, supply them to future MapReduce computations, or else use the digest to verifiably retrieve the actual data. Meanwhile, the verifier in the actual verification process never needs to handle the data itself, which is one of the coolest things about this. The way we do this is going to take more time than I have, so I will just I've been talking for 18 minutes, so I am just going to quickly show you a graph. What this graph is showing is that the verifier breaks even in the sense of saving CPU cycles from using this framework. Again, the verifier never needs to handle the actual data. Pantry applies pretty widely, not only to MapReduce, but also to verifiable queries on remote databases. We can even have the state that the worker's holding be kept private using and leveraging the machinery of Pinocchio. Our code base for Pantry works without modification for both Zatar and Pinocchio. To quickly just sum up the performance problems in the area, we have high setup costs for the general purpose systems, but those can be amortized in a cloud computing context. There are high verification costs. If our baselines are not optimistic, unfortunately, none of the systems are beating native execution, but that's okay because saving CPU cycles isn't everything. There's also saving network costs and saving storage costs, and using something like Pantry, we can in fact save storage and network costs even if the CPU costs are a little bit more expensive than we'd like. Worker overhead is still a little bit of a bummer in this area, and the computational model, despite many improvements, is still a toy. So there's three takeaways I'd like you to have from this. The first is that one way to organize the exciting work in this area is performance versus expressiveness. The second is that our work on Pantry extends the verification machinery to real computations that people use the cloud for. And the third is that there are a number of open problems for all of the systems that would be juicy research problems. And these juicy research problems actually span systems theory, parallel computing, and so forth. So it's an exciting time for the area. And I'd like to conclude after 20 minutes exactly with that.
All right, so why don't we start with a question or two for Mike, and then we'll open up to all three of the panelists and try and speed things along here.
So about these batch operations, is it possible that multiple users share the same key and use the same computation? And if so, what will be like security implications for those users?
So that's a great, the question is, in the batched model, can we have it be the case that multiple clients could be submitting their computations into the batch? Does that work, or what are the security implications? And the answer is, if you use what's known as the designated verifier schemes, which is Pepper, Ginger, Zaatar, or Pinocchio in designated verifier mode, then multiple clients can submit into the batch, but they all need to trust each other. They all have to be part of the same trust domain. If you want the clients to be mutually distrustful, you want a actually, they're still going to have to trust.
Public verifier.
Yeah, well, but public verifiability, yeah. Then you could use Pinocchio's public verifiability, and then the clients don't have to be mutually mutually trusting, but they have to believe that the proving entity or the worker didn't have access to the cryptographic material in the private part of the key.
Trust the key generation process.
Yes, they have to trust the key generation process, but not each other.
Okay. More questions? And since we're getting close to lunch, maybe we should just open it up to general questions. I think Tom?
Yeah, so I mean, it's a lot of talk about performance improvements, a lot of exciting work. Can you guys speak more about like exactly the threat models and how the nuances here, and what you expect in terms of deployment scenarios where people are really going to be concerned that outsourced storage providers or outsourced computation providers are maliciously modifying code, and if there's been thoughts about benign failures in this type of
I mean, as Brian said, I personally don't like the word malicious because it kind of raises the bar on when you'd want this. Verifiability is about protecting against bugs, misconfiguration. I mean, lots of things can go wrong that I wouldn't call malicious. So if the question is when does that happen, I mean, I don't know. When people use the cloud today, there's bugs, there's buggy hardware, there's lots of situations in which we might like a guarantee. You know, if we take a robot and send it off into outer space, you might like to know that it's computing properly without necessarily believing that NASA has all these malicious employees embedded in it.
Or that the Martians have hacked into your rover. I think it's a good question because I've talked with various CSOs who've come to visit Microsoft, and very few of them are worried about cloud. Surprisingly few are worried about cloud security in general, and those that aren't that worried about integrity issues. But I think if you present it to them in this framework, they aren't that interested. If you present this to them as a way of checking to make sure that the results coming back are correct, they're much more interested. You know, so they see it more as making sure everything hasn't gone wrong, or as an auditing tool that they might use occasionally to check to say, okay, in general things look good. But I don't think they're worried about Microsoft actively getting in there and tampering with the data. I think the only case where you might be worried about that would be if in the peer-to-peer setting, right, which is what sort of started me off in this area, was thinking about things like SETI at home or folding at home, where you just have random people on the internet contributing computation, you know nothing about them, and you want to check the results that come back.
Right, and the thing he's talked about, you could imagine doing randomized checking, so you won't actually check every computation, but you'll use it as an auditing tool, so you may check, you know, every 100 computations, and just to check if there seem to be errors going on.
Any other question?
Yeah, so this is sort of a naive question. You mentioned that everything that has happened so far has been for straight line programs. Is that true? What happens for programs where there's a lot of branching? Does the worker learn based on the branches that went this way versus the other? I mean, is that kind of primacy already taken care of in this setting?
So in general, none of the approaches we've discussed, at least in terms of implementation, provide privacy. So the worker knows everything about the computation.
I see. Okay.
And so for dealing with loops and that kind of thing, or branches, everything just gets unrolled. So you execute both sides of the if else, you execute the maximum number of possible iterations of the while loop. So that's why all three of us, you heard us say we want to move away from the circuit model, because that really sucks for a lot of computations.
Just as a technical point, the worker can short circuit, but the actual key lengths and setup costs are proportional to the sum of the code in the branches as a minor point.
Bruce?
I'm pretty loud.
That's all right. They need it for recording.
Thanks, Brian. So in your answer to the previous question, though, you said, well, what we've talked about today doesn't, these schemes don't provide any privacy. That is, the worker can see the computation. But there has been work, some of the original work on homomorphic encryption was geared at providing that kind of privacy. So I'm just curious, have you guys or others also been working on trying to make those systems with the stronger privacy guarantees more practical?
Not us specifically.
I personally have not. I mean, my group and I have really been focused on the question of integrity since It seems like it would be really cool, and it's required a lot of work to do. I think Brian might be the most natural person to answer that, being as he was the P in the GGP paper that applied fully homomorphic encryption to this problem, providing privacy.
So I guess the main answer is there's a ton of work going into making fully homomorphic encryption more practical. And there was certainly a lot of room to begin with, and there's still a lot of room for continued improvement. So I think at a high level, it hasn't, put it this way, the FHE schemes have not improved enough that I am excited about going off and implementing a scheme based on FHE. I think it's going to be several more years, if not a decade, before those become competitive. Now, there are alternate schemes like the one that we built on attribute-based encryption that might provide some degree of hiding, but even those at the moment, at least if you want general-purpose systems, just are not competitive.
And one of the things that I think comes out is that we've all approached this at slightly different angles. And you can see the systems have different properties. And fully homomorphic encryption, it's not quite clear when you get it to a practical level what those systems will look like and exactly what properties that they'll have. But my guess is that it will prove to be another point in the trade-off space. And so one of the things that's exciting about having these multiple groups working on it is we seem to be hitting different points in the trade-off space. And now there's some hope that, as we continue to progress, we'll get things that improve in all dimensions, or that combine the best of the possible ideas of all these different techniques. But my guess is still at the end of the day, there's going to be multiple sets of techniques that you could conceivably use that are going to offer different sorts of trade-offs in terms of the speed versus the expressibility versus the other sorts of things you might look for in the system. And so as fully homomorphic encryption becomes more practical, it'll be interesting to see what it gives you, on this trade-off space and what are the values it provides.
I guess one final note is that even though this has been entirely a talk about proofs based on cryptography or inactive proofs, there are, of course, other techniques you can use, right? There are auditing, there are
trusted hardware,
Byzantine fault tolerance, there's trusted hardware. And so if you're willing to make the assumptions that fit one of those categories, so if you're willing to say, okay, Microsoft's probably not going to tamper with the hardware, or you're willing to say, all right, Microsoft and Google both might try and screw me, but they might screw me in different ways, then you might be able to do better than some of the techniques that we've been presenting. So our techniques are really focused at the case where you don't want to make any assumptions, you just want to outsource your data and have a strong guarantee on the result. So I think we're running a little bit late for lunch. I don't want to keep you any longer, so thank you all for your attention.